Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating topic, evaluating frontier models for stealth and situational awareness.
Exciting stuff. The idea of AI operating discreetly and understanding its surroundings like a seasoned operative, that's the stuff of science fiction becoming reality.
It sounds exciting, but I think we need to pump the brakes a bit. Stealth and situational awareness are incredibly complex concepts, and I'm skeptical that current AI approaches are truly capturing what that even means.
I agree, there's a lot of hype, but the potential is there. I think the key is understanding how these models are representing the world, especially spatiotemporally. How are they understanding where things are in space and time, and how those relationships change?
Okay, so let's unpack this. When we talk about evaluating frontier models, what kind of models are we talking about specifically? Are we primarily focused on deep learning, or are there other architectures in the mix?
I think most of the current buzz is around deep learning, especially transformers. We've seen incredible leaps in their ability to process language, images, even solve complex problems. It's natural to try and apply that power to situational awareness, right? Think about self-driving cars. They need to understand their surroundings in real time to navigate safely.
Right, self-driving cars are a good example, but also a cautionary tale. They still struggle in unpredictable situations, which highlights the limitations of purely data-driven approaches. You can train them on millions of images, but they still might not understand the concept of a pedestrian stepping into the street. It's pattern recognition, not true comprehension.
And that's where the spatiotemporal understanding comes in. It's not just about recognizing a pedestrian as a pedestrian. It's about understanding their trajectory, their speed, their relationship to the car and the environment. It's predicting their next move based on a deeper understanding of physics and movement.
But aren't transformers getting better at that? They can now predict sequences, generate text that seems coherent, even anticipate human behavior to some extent. With enough data, can't they eventually learn to model these complex spatiotemporal relationships?
That's the big question, isn't it? My concern is that relying solely on brute force data might be missing some fundamental principles. We see stealth and situational awareness in the natural world, animals that can blend into their environments, predators that can anticipate their prey's movements. They're not doing it with terabytes of training data. There has to be a more efficient, biologically inspired approach.
Exactly. Think about a chameleon. It doesn't need to see millions of different backgrounds to change its color. It has a built-in mechanism, a set of rules, that allows it to adapt to its immediate surroundings. That's where neuro-symbolic approaches come in, combining the pattern recognition of neural networks with the explicit reasoning of symbolic AI.
Okay, I hear you. But the progress in deep learning has been so rapid. Remember when image recognition was a pipe dream? Now we have models that can identify objects in photos with near-human accuracy. Isn't it possible that with enough computational power and data, we can overcome these limitations?
Maybe, but I think we're hitting a wall. These models are incredibly good at pattern recognition, but they lack a deeper understanding of the underlying structure of the world. They're like incredibly sophisticated parrots. They can mimic intelligent behavior, but they don't truly understand what they're saying.
And that gets to the core of evaluating these models for stealth and situational awareness. How do we measure true understanding? It's not just about accuracy in identifying objects. It's about the ability to anticipate threats, adapt to changing circumstances, and operate discreetly without being detected.
Right. We need evaluation criteria that go beyond simple accuracy metrics. We need to test their ability to generalize to new situations, to reason about cause and effect, and to understand the consequences of their actions. Imagine an AI designed to infiltrate a secure network. It's not enough for it to simply recognize vulnerabilities. It needs to understand the potential risks and rewards of each action, and to adapt its strategy based on the network's responses.
So how do we define stealth quantitatively? Is it the probability of avoiding detection? The time it takes to complete a task without being noticed? How do we even measure that in a realistic setting?
I think a crucial aspect of stealth is the ability to operate in different coordinate systems. Imagine an AI controlling a drone. It needs to understand its position in GPS coordinates, its orientation relative to the Earth, the visual information from its camera, and the abstract representation of the mission objectives. It needs to be able to translate between all these different coordinate systems seamlessly and efficiently. And it needs to do it in a way that doesn't reveal its presence.
That's a great point, Donald. The ability to translate between different representations of space and time seems fundamental to true situational awareness. And it connects to my earlier point about threat assessment. If an AI can accurately model the environment in multiple coordinate systems, it can better predict potential threats and opportunities and react accordingly.
And that's where symbolic reasoning can play a critical role. You can encode explicit rules about how different coordinate systems relate to each other. For example, you can tell the AI that objects closer to the camera appear larger, or a sudden change in GPS coordinates indicates movement. These rules can help the AI to interpret sensory data and make more informed decisions.
But can't deep learning models learn those rules implicitly from data? They can learn complex relationships between pixels and objects, between words and concepts. Isn't it just a matter of scale?
I don't think so. I think there's a fundamental difference between learning a statistical correlation and understanding a causal relationship. A deep learning model might learn that when pixels in a certain region change rapidly, it usually indicates movement. But it doesn't understand why that's the case. It doesn't understand the underlying physics of motion.
And that lack of understanding makes them brittle and prone to errors. They can be easily fooled by adversarial examples, subtle changes to the input that cause them to misclassify objects or make incorrect predictions. A truly intelligent AI needs to be more robust and adaptable.
Exactly. That's why I think neuro-symbolic approaches are so promising. They allow us to combine the strengths of both neural networks and symbolic AI. We can use neural networks to learn patterns from data, and then use symbolic reasoning to interpret those patterns and make inferences.
Okay, so let's talk about specific examples. What are some concrete applications where stealth and situational awareness are critical? We mentioned self-driving cars, but what else?
Defense applications are an obvious one. Autonomous drones that can conduct surveillance missions without being detected. Robots that can navigate dangerous environments like disaster zones or war zones.
Cybersecurity is another big one. AI systems that can detect and respond to cyber attacks in real time without alerting the attackers to their presence. Think of it as an AI immune system for a network.
Search and rescue operations. Imagine an AI that can analyze satellite imagery to locate missing persons, even in dense forests or mountainous terrain. It needs to be able to understand the terrain, the weather conditions, and the potential search patterns, all while operating discreetly to avoid alerting the missing person if they're in danger.
And what about more mundane applications? Inventory management in warehouses. AI systems that can track the movement of goods without requiring manual scanning. Or even personalized advertising that's so subtle and relevant that it doesn't feel intrusive.
Okay, so we've established that stealth and situational awareness are critical for a wide range of applications. And we've discussed the limitations of current deep learning approaches and the potential of neuro-symbolic methods. But how do we actually build these systems? What are the key research challenges?
I think one of the biggest challenges is developing better ways to represent knowledge. Current knowledge representation techniques are often too rigid and inflexible. We need systems that can learn and adapt their knowledge representations over time.
I think the key is finding a way to represent spatiotemporal relationships in a way that's both efficient and expressive. We need algorithms that can translate between different coordinate systems seamlessly and understand the underlying physics of motion.
I think we need to focus on developing more efficient data acquisition and processing techniques. We need to find ways to train deep learning models on smaller datasets without sacrificing accuracy or generalizability. And we need to develop better ways to extract meaningful information from raw sensory data.
And I think we need to draw more inspiration from the natural world. We need to study how animals achieve stealth and situational awareness and try to replicate those mechanisms in AI systems. We need to understand the neural encoding of threat and opportunity assessment and how that information is used to guide behavior.
Yes, and we need to be careful about the ethical implications of these technologies. AI systems that are designed to be stealthy can be used for malicious purposes, such as surveillance or manipulation. We need to develop safeguards to prevent these technologies from being used to harm people.
Absolutely. The potential for misuse is a serious concern. We need to have open and honest conversations about the risks and benefits of these technologies, and to develop regulations that ensure they're used responsibly.
It's a double-edged sword. The same technologies that can be used to protect us can also be used to control us. It's up to us to ensure that these technologies are used for the benefit of humanity.
Okay, so let's wrap up by discussing some specific research directions. What are some areas that you think are particularly promising?
I'm excited about the potential of generative adversarial networks GANs to improve situational awareness. GANs can be used to generate realistic simulations of the environment, which can then be used to train AI systems. This could be particularly useful for applications where it's difficult or expensive to collect real-world data.
I'm interested in exploring the use of knowledge graphs to represent complex relationships between objects and events. Knowledge graphs can be used to reason about cause and effect, to predict future events, and to generate explanations for observed phenomena.
I think we need to develop new algorithms for translating between different coordinate systems. This could involve using techniques from differential geometry or topology to model the relationships between different spaces.
And I'm focused on understanding the neural mechanisms of stealth and situational awareness. This could involve using techniques from neuroscience, such as fMRI or EEG, to study how the brain processes information about threats and opportunities.
Another research direction could be looking into attention mechanisms beyond those currently used in transformers. Maybe something that can focus not just on what's important, but why it's important, building a causal understanding.
On the data side, I think a big area will be unsupervised learning. If we can get these systems to learn to model the world without explicit labels, it could drastically reduce the amount of data needed for training.
Building on the idea of different coordinate representations, I think we need algorithms that can handle uncertainty in those transformations. Real-world sensor data is noisy, so the system needs to be able to account for that uncertainty when translating between spaces.
I'm also interested in how we can formally verify the safety and reliability of these systems, especially when they're deployed in safety-critical applications. How can we be sure that they won't make mistakes that could have serious consequences?
That's a great point. Formal verification is crucial. We need to develop tools and techniques that can help us to reason about the behavior of these systems and to ensure that they meet certain safety standards.
And explainability is key. If we can't understand how these systems are making decisions, we can't trust them. We need to develop methods for making AI systems more transparent and interpretable.
Ultimately, I think the goal is to build AI systems that are not just intelligent, but also responsible and ethical. We need to ensure that these technologies are used for the benefit of humanity, and that they don't exacerbate existing inequalities or create new ones.
Well, this has been a fascinating discussion. It's clear that there are many exciting research challenges ahead, but also great potential for these technologies to improve our lives. Thanks for joining me today.